Hey everyone, Katrina here, and today I'm going to show you how to graph tricky rational functions. Make sure that you subscribe and watch to the end to see the full example unfold. Okay, so we're going to dive in with an example. So we're going to consider some function f of x equals to x minus 1 over x squared minus x minus 6. Okay. I really encourage all of you to check out my previous video, which talks about all the different cases, how to find horizontal asymptotes when you have rational functions. This video breaks down the three main cases and a strategy that you can use every time. So I'm going to be referencing that for a bit of a strategy here. And today we're going to be more focused on going through an example and learning how to graph it from start to finish. So whenever we're trying to graph a rational function, I always encourage you to write down the 6 main key aspects of a function that you always need to have. So let's kind of write that down. So we want our key features, I guess we'll call that. So this kind of helps us organize ourselves when we're trying to solve these problems, because I don't know if you can, but looking at this question over here, I can't graph this from the top of my head. I need to go through a strategy and get as much information as I can from this function. So the key, sorry about that, the key features we want to look at is the x-intercept, so we'll call that number 1. Number 2, we want the y-intercept. Number 3, we want the horizontal asymptote. Number 4, we want the vertical asymptote. And then number 5, we want the domain. And then number 6, we want the range. So just so you know, the range is not always possible to find unless you're using calculus. So I do have another video on curve sketching and optimization, and that one over there, it will help you find the range. So I'll just see curve. Oh my goodness, curve sketching video. We might be able to find it, but there are some cases where you can't. You have to use other techniques, like the first derivative, to figure out where your local maximums and minimums are. So today's lesson is more for like an advanced function type level, where we're trying to graph something given key features of a function. Okay, so finding the x-intercept, let's go through that. So to find that, what we have to do is set y equals to 0 and solve for x. Okay, so when y equals to 0, what do we have in our case? We've got 0, and then that means our whole denominator here is going to be multiplied by 0, so it disappears. So 0 equals to x minus 1. We're going to solve for x, and what do we get? X equals to 1, so then our x-intercept is some point 1, 0. Make sure that you write out the ordered pair. Y-intercept, same but opposite. We're going to set x equals to 0, and then we're going to solve for y. So let's go ahead and do that. When x equals to 0, we have that y equals to 0 minus 1 over 0 squared minus 0 minus 6. So that is just simply negative 1 over negative 6, which equals to 1 over 6. And then again, we'll write out our ordered pair. So we have 0 and 1 over 6. Amazing. So we already have 2 anchor points on our plot. Okay, horizontal asymptote. So this is where I said reference my video on finding horizontal asymptotes. I'll give you a sneak peek. If the degree of the numerator, so we're going to call that n, is less than the degree of the denominator, which we're going to call m, then we're going to have a horizontal asymptote at y equals to 0. And in this case, the degree of our numerator is 1, which is less than the degree of our denominator, which is 2. So therefore, we're going to have horizontal asymptote at y equals to 0. Now our vertical asymptote. So vertical asymptotes are actually pretty nice to solve for. Again, horizontal and vertical asymptotes, you can always use limits to solve for them. But another quick trick for vertical asymptotes is you can set your denominator equals to 0 and then solve for x. So in this case, we have a quadratic, so we're going to have to factor that first. Again, if you need help factoring, I have a whole crash course on factoring, so be sure to check that out in the factoring playlist. So here we've got x squared minus x minus 6, we can use a product sum rule. What do we have? We have that the product equals to -6 and the sum equals to -1. So what two numbers multiply to -6 and add to -1? So 2 and -3 work. That means this can be factored as x plus 2 and x minus 3. If we set that equal to 0, then we have that x equals to -2 and x equals to 3. So those there are going to be our two equations for our vertical asymptotes. So we have two vertical asymptotes in this case. Now we're going to look at the domain. So the domain is neat because you want to look because it correlates with your vertical asymptote. Vertical asymptotes are vertical lines in which your function cannot exist. They're lines which your function will approach and get infinitely close but never actually touch. So that means wherever you have a vertical asymptote, well, that's an x value in which your function cannot exist. So that means for your domain, you'll have, in set notation, you'd write it as x is an element of the real numbers, and then you're going to show your restrictions. So obviously, if your function cannot exist at a vertical asymptote, those will be displayed as restrictions in your domain. So that means that x can be any real number such that x cannot be equal to -2 and x cannot be equal to 3. And our range, so in this case, we have a bit of a more regular value in the sense that we have a horizontal asymptote, but we also have an interesting case here. I would call this a little trip down the rabbit hole because we actually have an x-intercept. So let's kind of explore why this is weird. So we've got an x-intercept here at x equals to 1. So that means we have some point on our graph where x equals to 1 and y equals to 0. But we also said that we have a horizontal asymptote when y equals to 0. And horizontal asymptotes are supposed to be lines in which your function does not exist. But we have entered some interesting and odd case such that our function will cross our asymptote. So just so you know, that is possible. There are times where functions may cross asymptotes. However, in terms of end behavior, you would say that your function infinitely approaches your asymptote, gets infinitely close without actually getting there, but in the in-between space, that's not the end of your function, it is possible that it could cross. So this over here, this is kind of like a big thing showing us that our function crosses the horizontal asymptote. So since it crosses the horizontal asymptote, what does that mean for our range? Well, just like the domain is closely related to the vertical asymptote, you say that our range is closely related to our horizontal asymptote, such that where you have a horizontal asymptote, that's a restriction in your range. But in this case, this is an exception because our function crosses the horizontal asymptote, so it can exist within our range. Therefore, we have that y can be an element of the real numbers and there's no other restrictions that we have to worry about. Okay, now that we have our 6 key features already found, let's go ahead and work on plotting this. So I usually like to follow this order, and that can sometimes help me write it out. So I also apologize if my lines are a little bit shaky, but we will try our best here. So we've got our x-axis and we have our y-axis. So let's put on all the information that we know. Okay, I like usually putting my asymptotes first. So let's see, we have remember this again is a rough sketch. We're going to have one vertical asymptote at -2. So let's call this line over here in yellow -2. And then we also have another vertical asymptote at 3. So 1, 2, 3, somewhere over here. And then we have a horizontal asymptote at y equals to 0, which is right over there. Okay, and now the second thing I like to do is put down my anchor points, which I have as my x and y intercept. So I know I have an x-intercept at 1, so right over here. so at 1. And then I also have a y-intercept at 1 over 6. So we'll just kind of put an approximate 1 over 6 right over there. And those are my only two times where my function is allowed to cross either my x or y-intercept. So we can use that accordingly to help us kind of draw out this function. So, okay, what's going to happen here? So where is our function going to exist? Well, you can always write out table of values if you need more help. So table of values, and that means that you can set up some x and y, and then you can go through various numbers of x, the independent variable, and see what values of y you get. But here I'm going to work on kind of following my key points to see what I have. So I know that my function wants to get close to my asymptote, and I know it can only cross this y-intercept once. So that means that it's going to come down like this. Let's try that again. So it actually hits the intercept. And then it has to hit the x-intercept, and then I know it's going to be approaching the vertical asymptote again down there. Okay, so then where are my other functions going to be found? So in this case, we don't really know which quadrant right now just by looking at it is the function going to exist. Because we know that it can exist, it's going to exist for all values of x except for the two asymptotes. So this is where you can kind of check a couple points and see what's your function going to be. So what does that mean? Let's kind of test one here. So we're going to test f at negative 2.01 because we want to look on just the left side of our asymptote. We want to know, is our function going to be positive or negative, because that's going to tell us which side of the asymptote it's going to be on. And if you plug that into your calculator, you'll get a number approximately negative 60. So that means that we know our function has to exist in this negative quadrant over here, because just a snitch left of negative 2, we're already going to be down at negative 60. And we know we can't cross this horizontal asymptote anymore, so we know our function is going to exist something like this. And remember, since this is a function, not a relation, for each value of x, we can only have one value of y, so that means we can erase this question mark up there. Okay, now looking at our other side, where is our function going to exist? So we can check f of, let's try just to the right of 3, so f of 3.01. We're going to get something approximately equal to 40, which is positive. So we know that at 3.01, our function is going to be existing up here. And we know it can't cross these asymptotes because we have no other x or y intercepts. So it's going to continue down along this line. And again, just like before, it's a function. For each value of x, we can only have one value of y, so we can erase these question marks. The last thing that you can look at is just kind of test your end behavior to see how your function is. So you can just like plug in an approximate number of, let's just say minus 500, something quite large in the negative direction, and we'll get negative 0.041. So what that tells us is that our function stays below the x-axis over here. So we know that as it continues on infinity, it's staying below our line. So if this is our axis over here and this blue line is a continuation of our function, we know that it's going to stay on the negative side. Let's try it up here. So, sorry, that tells us that it's not going to cross the axis again. And what about here? What if we try f of 500? We get 0.002 approximately, so that means it's going to stay positive, so it's staying above the axis here as x goes to infinity. So it's always good to check that just to kind of look approximately at the end behavior of your function. So this is a bit of almost a cheat way if you don't want to take the limit. Sometimes you might have not learned limits yet in class, so you can just plug in an arbitrarily large number just to see kind of what that approximate end behavior of your function is. Is it going to be positive, negative, above or below the x or y axis? And that really kind of helps teach you a lot. The last thing that you can do if you want is add more anchor points to your plot. So what that means is just like try a couple x points, maybe plug in x equals to 4 and see what is y equal to get another point. Same thing here, you can try plugging in x equals to negative 3 and see what is your y equal to, just so you have a few more anchored points on your plot, which just gives a higher accuracy of your plot. And again, this is more of a sketch. This helps you understand key features of your function, such as domain and range, and also the end behavior and the behavior with respect to the asymptotes, and it gives you an overall shape of your function. So I hope that helped you. This is like a pretty good guide if you're trying to plot rational functions. And again, make sure to check out my other video about horizontal asymptotes if you want to learn more about those, and also check out my curve sketching videos. That's kind of the next level of this type of video, where we're using calculus, derivatives, second derivatives to get a more accurate understanding of all types of functions, as well as understanding maxima, minima, and optimization techniques and facts. So if you enjoyed this video, please give it a like and comment any questions that you have, and definitely subscribe for more videos. I look forward to seeing you next time.